Dear students, in this video we are going to see about the temperature dependence of resistivity, temperature coefficient of resistivity of conductors and semiconductors.
Temperature dependence of resistivity. The resistivity of material is dependent on temperature. It is experimentally found that for a wide range of temperatures, the resistivity of the conductor increases with increasing temperature according to this expression rho T equal to rho naught 1 plus alpha T minus T naught, where rho T is the resistivity of the conductor at T degrees Celsius and rho naught is the resistivity of the conductor at some reference temperature T naught, usually at 20 degrees Celsius. And alpha is the temperature coefficient of resistivity. Now, how to define this temperature coefficient of resistivity? That is defined as the ratio of increase in resistivity per degree rise in temperature to its resistivity at T naught. From the equation 2.27, we can write rho T minus rho naught equal to alpha times rho naught into T minus T naught. Therefore, alpha, the temperature coefficient of resistivity, is given by the expression rho T minus rho naught by rho naught into T minus T naught, and that can be written as delta rho by rho naught into delta T, where this delta rho is given by rho T minus rho naught, that is the change in resistivity for a change in temperature delta T, that is given by T minus T naught. This unit is per degree Celsius. Now, we will see about the resistivity of the conductors, that is given by positive value for conductors. Alpha will be always positive. If the temperature of a conductor increases, the average kinetic energy of electrons in the conductor increases, and this results in more frequent collisions, and hence the resistivity also increases. The graph of the equation 2.27 is shown in this figure 2.13 here, and even though the resistivity of conductors like metals varies linearly for a wide range of temperatures, there also exists a nonlinear region at very low temperatures. The resistivity approaches some finite value as the temperature approaches absolute zero, as shown in figure 2.13b. Yeah. Then, by using the equation rho equal to R times A by L in equation 2.27, we get the expression for the resistance of the conductor at the temperature T degrees Celsius as RT equal to R naught 1 plus alpha into T minus T naught. The temperature coefficient of resistivity can also be obtained from the equation 2.28. So RT minus R naught equal to alpha times R naught T minus T naught, and alpha is given by RT minus R naught by R naught T minus T naught. That's given by 1 by R naught into delta R by delta T. So the temperature coefficient of resistance that's given by alpha equal to 1 by R naught into delta R by delta T, where this delta R is given by RT minus R naught. This change in resistance during the change in temperature delta T equal to T minus T naught. And alpha of semiconductors. For semiconductors, the resistivity decreases with increase in temperature. As the temperature increases, more electrons will be liberated from their atoms. And the graph will be like this. Hence, the current increases and therefore the resistivity decreases as shown in this diagram. A semiconductor with a negative temperature coefficient of resistivity is called a thermistor. So you can write this answer for the question, what is a thermistor? The typical values of temperature coefficients of various materials are given in this table column. For example, silver has the temperature coefficient of resistivity as 3.8 and power minus 3 degrees Celsius. And we can understand the temperature dependence of resistivity in the following way. Yes, in section 2.1.3, we have shown that the electrical conductivity is given by sigma equal to n e squared tau by m. As the resistivity is inverse of sigma, it can be written as rho equal to m by n e squared tau. So the resistivity of materials is inversely proportional to the number density of the electrons, and it is also inversely proportional to the average time between the collisions tau. So in metals, if the temperature increases, the average time between the collision tau decreases and then is independent of temperature. In semiconductors, when temperature increases, n increases and tau decreases, but increase in n is dominant than decrease in tau, so that overall resistivity decreases. The resistance of certain materials becomes zero below a certain temperature Tc. This temperature is known as critical temperature or transition temperature. The materials which exhibit this property are known as superconductors. So this phenomenon was first observed by Cameron Owens in 1911. He found that mercury exhibits superconductor behavior at 4.2 Kelvin. Since R is equal to 0, current once induced in a superconductor persists without any potential difference. So they are called as superconductors.
You need to hear this if you're into gadgets and tinkering. When your device heats up, its wires aren't the same anymore. Temperature tweaks how easily electrons flow through a device. That can make device performance shift. It can shorten a device's lifespan. Resistivity is how much a material fights electric current. In metals, heat makes atoms jiggle and vibrate. Those vibrations scatter electrons, increasing resistivity. So wires get worse at conducting as they warm. In semiconductors, more heat frees charge carriers. That lowers resistivity, up to a point. Engineers balance these effects with cooling, with material choice, and careful design keeps devices reliable. Bottom line, temperature isn't just a number. It changes how electricity behaves. Keep it cool, and electrons will thank you.